Good morning, students. Myself, Dr. Rajwant Kaur, lecturer in chemistry at Government Polytechnic College for Girls, Amritsar. Our today's topic is softening of hard water. In the previous lecture on Wednesday, we have discussed the problems of using hard water for domestic as well as industrial purposes. Today we will be discussing how to soften hard water. Hard water poses many problems when used in boilers for industrial purposes. It has to be softened before using in boilers for the steam production and in other industries also. Various methods are employed for softening of hard water. After examining the cause of hardness or the salts or the ions responsible for hardness of water. The main methods, or if we want to say what is softening of hard water, then we can define softening of hard water as the process to remove hardness causing ions from water. We all know that hardness of water is due to the presence of substances like soluble bicarbonates, chlorides and sulfates of calcium and magnesium in water. So, before using water, we have to remove all hardness causing substances from it. Now, this process of removing hardness of water is called softening of hard water. Now, the methods which are basically used for softening of hard water, there are many methods, but in this lecture we will be discussing the important three, namely permutate or zeolite process, then ion exchange process and RO process or reverse osmosis process. Ion exchange process is also known as demineralization process, and reverse osmosis process is one of the methods for desalination of seawater, that is the removal of sodium chloride from the seawater to make it fit for human consumption as well as for industrial use also. Now, we will be discussing these three methods one by one. To start with, we are dealing with permutate or zeolite process. Permutate is the technical name given to sodium zeolite. The formula for the sodium zeolite is Na2Al2Si2O8 XH2O, means the number of moles of water of hydration can vary and its value may change from vary from 14 up 10 to 14. In general, we can represent sodium zeolite by a formula Na2Z, where Z stands for all this, that is Al2Si2O8 XH2O. Now, the permutate is Na2Z or sodium zeolite. In the coming chemical equations, we will be representing permutate by this formula, that is Na2Z, where Z stands for Al2Si2O8 XH2O. Now, this permutate is naturally occurring as well as it can be prepared artificially. In order to prepare permutate for trading, it is prepared by fusing a mixture of soda ash, that is sodium carbonate, silica having formula SiO2, and alumina, that is aluminium oxide or Al2O3. Now, when we fuse this mixture, we get a fused mass which is then washed with water, and after washing, the porous mass which is left, that is called permutate. Now, this was about the preparation of permutate. Once we have the permutate, in order to purify water, the hard water is passed through the bed of permutate contained in a suitable vessel. Water first reaches the bottom of the vessel, and as it rises up, the suspended impurities are removed by coarse sand. Basically, in the vessel, we have coarse sand at the bottom, and then we have a layer of permutate. Water is first passed to the bottom, it reaches the bottom of the vessel, and then it rises up. As it rises, the suspended impurities are removed by coarse sand, and when it passes through permutate, the calcium and the magnesium ions which are present in hard water and are responsible for the hardness of water, they are exchanged with sodium ions. Sorry, here it should be Na positive, not Na2 positive. It is Na1 positive only, univalent ion. Then this is the, you can say, diagrammatical representation for the permutate process. In this case, water enters in the vessel, reaches the bottom, and then rises up. This layer is the sand or gravel layer. The suspended impurities are removed in this layer. This portion is represented by the permutate layer. When the water rises up through this layer, then the calcium and the magnesium ions which are responsible for hardness of water, they are exchanged with the sodium of sodium zeolite, and the softened water that is collected over here can be removed through this vessel by having a tap over here. Now, as we go on softening the water through the same bed of permutate, ultimately the permutate gets exhausted. It means whole of the sodium ions, they are exchanged with calcium and magnesium ions, and at this stage the zeolite or the permutate is not effective in removing the hardness of the water. Now, when whole of the permutate gets exhausted, then it is regenerated. Now, the regeneration of the permutate is done by passing brine solution, that is sodium chloride, 10% solution of sodium chloride. When we pass brine solution and remove the waste from this lower tap, then whole of the calcium and the magnesium ions, they are converted into calcium or magnesium chlorides and are removed with wastewater, and the permutate is again regenerated, or we can say that we can use it again and again by washing it with sodium chloride. Now, these are the chemical equations representing softening of hard water using permutate or the zeolite process. In this case, this is permutate or sodium zeolite. When we pass hard water through this, then the sodium ions, they are exchanged by the calcium, and we get, in this case also, here it should be only univalent sodium ions, not the bivalent one, and this is our exhausted permutate, or the calcium ions or the magnesium ions which are responsible for hardness and are present in hard water, they are exchanged with sodium of sodium zeolite, and we get calcium and magnesium zeolite which is retained, and in water we have sodium ions which do not cause any hardness, or we can say this water is soft because it will form leather easily with soap. Now, in this slide we are giving the process of regeneration of permuted. As I have already told you that when after a long use permutate is exhausted and it is completely changed into calcium and magnesium zeolite, then it will not be able to soften water further. In this case, the permutate is made active again by passing 10% solution of sodium chloride. Now, this solution is known as brine solution through it. These are the equations which represent the regeneration of exhausted permutate. Now, this is calcium zeolite and magnesium zeolite, means the permutate which cannot soften water further, exhausted permutate. When sodium ions from sodium chloride, that is brine solution, they are exchanged with calcium and the magnesium ions, and we get regenerated permutate which can then be used for softening hard water. No doubt zeolite process has many advantages, but it has certain limitations also. The limitations include that it cannot be used to treat saline water. The reason behind is saline water contains sodium ions, and the sodium ions cannot be exchanged. They are already sodium in case of sodium zeolite also. Because of this reason, it cannot be softened, or you can we cannot say that we in this case we cannot treat saline water with zeolite process. Another limitation of zeolite process is that acidic water, means the water which has low pH value, cannot be treated through this process. The reason behind is that acid in the acidic water destroys the zeolite bed. If we want to treat this acidic water with this process, we have to first neutralize the acid, and this neutralization is done by washing by treating the water with washing soda. Another limitation of zeolite process is turbid water cannot be treated with this process. The reason is the turbidity clogs the pores of the zeolite bed, and as the pores are clogged, then the zeolite bed becomes inactive and we cannot soften water, soften turbid water with this process. So, if we want to soften turbid water or treat turbid water with this process, we have to remove suspended particles which are present in turbid water, first by coagulation and then by filtration. Only then the coagulated and filtered water can then be treated with this process. Another limitation is that if the water contains high amounts of manganese and iron ions, ferrous ions, then this water can also not be treated through this process. The reason is that manganese and the ferrous zeolite which are produced by passing this water through the zeolite bed, they cannot be regenerated easily. They form permanent complex, sort of permanent complex that cannot be regenerated by washing with sodium zeolite, and as such this water cannot be treated with zeolite process. Another limitation that this zeolite process cannot be used to remove microorganism or kill microorganism or other impurities which do not ionize in water. Only the ions, positive ions like calcium and magnesium can be removed through this process. The impurities which do not ionize like microorganisms or other vegetative or organic impurities which are present in water, they cannot be removed through this process. Now, coming to advantages, we have already discussed in our lower classes the lime soda process for softening of hard water. This zeolite process is more efficient than the lime soda process for softening of hard water. Another advantage is that the equipment which we use in this process, that is very compact as compared to the equipment that we use in lime soda process. This is a comparison with the lime soda process which we have already studied in our lower classes. Another advantage of zeolite process is there is no danger of sludge formation, because in case of lime soda process there is lot of sludge formation which has to be removed from time to time. So, in this case there is no such sludge formation in zeolite process. This process requires less time for softening hard water, means the water is passed, reaches the bottom, rises up, and in this process only the water gets softened. Another disadvantage, coming back to disadvantages, the treated water, as we already know that the calcium and the magnesium ions, they are exchanged by the sodium ions. It means the treated water contains more sodium salts than the lime soda process, because in that case we do not have any sodium ions, additional sodium ions present. Further, the treated water removes only the calcium and the magnesium ions or the cations only. All the anions which are present in water, they remain as such, and as a result they may cause problems in boiler feed water. Now, the problems, basically all these ions, they are responsible for the formation of acids in water, and these acids are then responsible for the corrosion of the boiler material. Now, the next process is the ion exchange method. As the name indicates, in this method we exchange the ions with hydrogen ions and the hydroxyl ions of water. In this process, as we know that we have to change ions, it means we have to change both the cations as well as the anions which are present in hard water. For this process or for this method, we require two types of resins. Resins are nothing but they are the cross-linked long chain organic polymers which have ionizable functional groups at one end. Now, these ionizable functional groups are basically responsible for ion exchange with the ions which are present in hard water. These, depending upon the ionizable functional group, these resins are of two types. One is the cation exchange resins and other is anion exchange resins. Cation exchange resins, they exchange the cations which are present in hard water like calcium and magnesium with H ions, and anion exchange resins, they exchange the anions like chloride, sulphate, bicarbonate which are present in water with hydroxyl ions. Now, cation exchange resins are organic polymers which have ionizable groups like carboxylic group or sulfonic acid group which are present at one end, and they can exchange their H ions with cations like calcium and magnesium which are present in hard water. Mainly these resins are styrene divinyl benzene copolymers, because they are the polymers which on carboxylation or sulfonation, when we carboxylate we get carboxylic acid group over there, and when we sulfonate it we get the sulfonic acid grouping over here. Now both these groups they can exchange their H ions with calcium and magnesium ions. For writing chemical equation or for representing them, in general we represent them like H ions dash resin, means the polymer can exchange this H ion with the cations which are present in water. Anion exchange resins, as the name indicates, they can exchange anions present in water with hydroxyl groups. Now, for exchanging anions with hydroxyl group, these resins have functional groups like hydroxyl group and amino group at one end. Now, when these on treatment with sodium hydroxide, they become basic and can exchange hydroxyl groups with the anions like chloride and sulfate ions which are present in hard water. Now, resins, as in the case of cation exchange resins, they are also styrene divinyl benzene or amide formaldehyde copolymers, but in this case they contain amino or quaternary ammonium groups. Now, these groups on treatment with dilute sodium hydroxide contain replaceable, here it should be E, replaceable hydroxyl groups and become anion exchange resins. As we have represented cation exchange resins by general formula H ions resin, similarly we can represent these anion exchange resins by OH resin, which indicates that they can exchange this hydroxyl group with the anions which are present in water like chloride, sulfate, bicarbonate, etc. Now, these are the chemical equations for ion exchange process. Hard water is passed through a bed of cation exchange resins first. Now, when we pass hard water through cation exchange resins, then whole of the cations, all the cations like calcium, magnesium or other metals, they are exchanged by H ions. Now, the water which comes out from cation exchange resins, that is then fed to anion exchange resin. Now, these are the equations for cation exchange resin only. Calcium or the magnesium ions which are present in hard water as say chloride or sulfate, when they pass through cation exchange resin, this is the formula for the cation exchange resin, the H ions they are replaced by the calcium or the magnesium ions and we get calcium resin or magnesium resin, and in water now we have H ions and the anions, whether chloride or sulfate. It should, this 4 should be subscript over here like this. Now, when the water which has been treated or passed through cation exchange resin is then fed to anion exchange resin. This is the container for the cation exchange resin. Water is passed first through this resin. This layer is of gravel. The water which is coming out of this resin is then fed to anion exchange resin, and this is the water which we are getting does not contain any of the ions, whether cations or anions. It has only H ions and hydroxyl ions. Now, water coming out from the bottom of the first tank is free from cations causing hardness of water. It contains H ions, chloride ions and sulfate ions, and is then passed through the second tank packed with anion exchange resins. In the anion exchange resins, the OH ions, they are exchanged with chloride ions or sulfate ions which are present in hard water. Now, these are the chemical equations for when the water is passed through anion exchange resin. Chloride or the sulfate ions, when passed through anion exchange resin, the resin gets attached to chloride or sulfate, here it should be 4 sulfate, and we get in water only the hydroxyl ions, or we can say OH ions. Now, the H ions coming from the cation exchange tank, they combine with hydroxyl ions coming from anion exchange resin to form water. It means the water which is coming out of the anion exchange resin tank is free from all types of cations as well as anions which are responsible for hardness of water. This water, as we have removed all the minerals which are present, or we have removed all the ions other than H ions and the hydroxyl ions from water, this process is also known as demineralized water or deionized water. The water which we are getting from anion exchange resin is known as demineralized water or deionized water. Now, as in the case of permutate, when whole of the resin has replaced the H ions as well as the hydroxyl ions, it becomes exhausted and is no more in a capacity to soften water, then it has to be regenerated. Now, for regeneration of the exhausted resin, we employ different methods for regenerating cation exchange resin as well as anion exchange resin. For regenerating cation exchange resin, we treat it with dilute hydrochloric acid or sulfuric acid. When we treat it with dilute acid, we get regenerated resin. It should be written over here. This is calcium chloride. Regenerated resin is obtained. Now, regeneration of the anion exchange resin is done by washing with sodium hydroxide, dilute solution of sodium hydroxide. When we wash it with sodium hydroxide, we get regenerated resin, that is anion exchange resin. Now, coming to advantages of this process, it can be used for treating or for softening highly acidic or alkaline waters. This is an advantage over permuted process which cannot be used for acidic water. Further, this method gives us water of very low hardness, and as such it is very good for use in high pressure boilers where we require water of very low hardness. No doubt it has its own limitations also. The main limitation or the drawback of this process is that the equipment which we use in this process is very expensive, and the chemicals are also very costly which we require. No doubt we can regenerate them, but initial cost is very high. Further, if the water contains turbidity, then the output of the process is reduced. Naturally, the turbid water will clog the resins and will make it unfit for further use. Now, in order to overcome these drawbacks, we have another method, reverse osmosis process. This method can remove both ionic as well as non-ionic, colloidal, high molecular weight organic impurities also. Now, the basic principle of this process is osmosis. Now, what is osmosis? It is the process in which the water moves from its higher concentration to its lower concentration, means from a dilute solution water moves to a concentrated solution.